Hello, I hope you're having a nice afternoon. I'm John DeGonia. This is my lab for spring oscillation presentation. So the purpose of this lab, well, we'll be analyzing an object undergoing oscillating motion, and then from that object we'll be determining information like the time period and the spring constant. We'll construct a model that replicates movement and energy of that system, and then we'll show how kinetic energy and potential energy are related, and how the constant energy, or the total energy, including those, stays the same in a closed system. Relevant principles include the momentum principle and the spring force and oscillation. And then the simple harmonic motion of a time period, that's how we're going to be, this is the basis of the equation of how we go from our time period to get our k value. So initial factors, we've got initial position, initial velocity, mass of object, gravity. These are all given to us from the start. And then we take our time period to be 1.519 seconds. That's our y oscillation measured as the average of the first three. And then from that, we extrapolate k using the equations you've already seen before, and then get our L. So important elements of code. At the start up here, we're just going to be initializing some things. Then we're going to be calculating kinetic energy, potential energy, kinetic energy, potential gravitational energy, potential spring energy, and adding them all up to get total energy. Then, like previous labs, we're going to be calculating forces and adding them together to get a net force, then using the momentum principle to update velocity and predict motion. So we've got force due to gravity, force due to spring, add them together to get F net, and use that to update velocity, and use velocity to update position. Over here on the left, we're just updating their positions like we did in the start with our new motion. And then we'll be calculating energies. We've got the kinetic energy, the change due in that area, the potential gravitational energy and its change, and the potential spring energy and its change, adding it all together to get our total energy. So let's look at the data. Here we have total energy in orange staying constant the entire time, potential spring energy in green, and potential gravitational energy in red. As you can see, they trade off as it oscillates, and then kinetic energy in blue, changing according to motion. It's going oscillating twice as quickly on the graph here because every time it hits the end of an oscillation, the movement stops briefly, and that's when you have zero kinetic energy. Let's look at our data as far as motion. We've got our computer model in blue and our observed motion in red. They start near each other and begin similar motion. The blue model is smoother due to a high rate of calculation, but there are a few problems here. First off, the blue model seems to delay. It's got a similar time period, but it's not acting as quickly. And then also you'll notice that there's something wrong with our k value because the real life observed motion is oscillating much farther. We'll get to that in a minute. And then satisfaction of the energy principle. So our system is that of a closed system. It's got the spring, the weight, and the earth, and there's no energy being added to it or taken away from it during the oscillation. So that's why we have our total energy staying constant the entire time. And you can see, even though like spring energy is not always the same, for example, in this third oscillation here, or I should say second oscillation, it's a little lower, but that's just because in this particular instance, some of that energy is dedicated to kinetic energy. So why was our data funky? Why was the oscillation farther than it should be? Well, it has to do with how we're calculating oscillation. So I used the oscillation in the y direction, which had a time period of 1.519 seconds, and a k value of 6.878, or at least that's what I found. That's a little closer to the known value, although not exactly the same thing. If we look at x oscillation, because it's also oscillating back and forth horizontally, we get a different time period and a different k value. And because our model is not incorporating both the horizontal oscillation and the vertical oscillation, it's not giving us an accurate measure of exactly how this thing is moving. Our model just considers it to be bouncing up and down, and it's not worried about the reality that it's also being stretched side to side. So that's why our k value is a little different and is a probable source of error for our data. Other than that, I hope you have a nice day. Thank you.